Okay, so we were talking about a general position. Okay, so if I have here at this location, for example, this is UT. So they just can give you x of a. If they give you x of a, you will be able to determine everything. Why? Because look, if you know x of a, how you can determine the direction of UT? Who will tell me? This is UT. Why, if you know x of a, you will be able to know the direction of UT? Let me give you an example. If I tell you x of a is equal to 30 meters, okay? How you can find the direction of UT? What should you do? You know that UT is along the tangent line, okay? Yes, very good. It is the derivative, okay? So you have that UT is along the tangent to the path, okay? So the slope of the tangent is given by dy by dx, okay? So you can say that the angle done between UT and the horizontal, the angle theta here, is simply can be calculated by tangent minus 1 of dy by dx, okay? So for example here, if they gave us x equal to 30 meters, at x equal to 30 meters, if I replace in dy by dx is x over 30, then I will get that for xa equal to 30, tangent minus 1 of 30 over 30, which is 1, is 45. So at point A, what is theta? Theta is 45 degrees. Okay, so this will allow me to know the direction of UT. And since UN is perpendicular to UT, then I can find how is UN. Now, in this problem, if I want to draw the free body diagram, it is a little bit more complicated than the one at A, because as you can see, so this is UT. It's doing an angle of 45 degrees, so I can represent the horizontal. This angle is 45. I calculated from the position of A. So this is 45 degrees. Now, concerning UN, UN is perpendicular to UT. So this is UN. UT, UN. Okay. Now here in this problem, UB is perpendicular to the screen. Okay, but we will not need it. You know why here we will not need to write sum of B equals 0? Because we don't have any projection along UB, so it will not give us anything. So in general, when all forces of motion acting on the object are in the plane of motion, you don't need sum of B equals 0. You will only need it if you have forces that has projection that are not in the plane of motion. Okay? So, if I look at this figure here, the two forces are the weight, W, and the normal reaction. You know that normal is perpendicular to contact. And here the contact line is along the tangent line. So the normal end will be perpendicular to UT along UN. So this will be your normal. Then in this case, as you can see, the two forces are in plane UN UT, so they don't have any projection along UB. Okay, so I will not need to write sum of B equals 0. Now, what will differ in the projection we did? So here, for example, when we write sum of n equals MAN, we will not only have along UN, we have the normal reaction, okay, but we don't have the completely the weight, we have the projection of the weight. So in order to project the weight, we should know the angles. But here it's simple to find the angles because as you can see here, this is the extension of UN. You know that this angle here is 45 degrees, okay? And the weight is perpendicular to the horizontal. So this also will be 45. So this is 45. And since you have here between you, so the angle between the weight and UT is 45. And since the angle between UT and UN is 90, so also between the weight and UN, you have an angle of 45. So if you want to project the weight, what will change here is that you should put the weight W times cosine 45 equals to m times v square over rho. They can give you, they should give you the velocity. Okay. We will learn together how to get the velocity if they don't give it to us. We will do it. Okay. So v at B, I will call this point B. Let's say. Okay. أو حتى فيكم تسموه it's another point A. So A prime. Let's say. So velocity now at A prime, or it's given, or we should find it. And over rho of A prime. To get rho of A prime, all we have to do is to replace x by its value of 30. Okay, so dy by dx, we have calculated already, it's 1. And the second derivative is equal at any location, so it's 1 over 30. Then knowing the first and the second derivative at A prime, we can calculate rho, and then we get the equation number 1. The second equation will be the projection along UT. So here it's not anymore 0 because as you can see in the figure, the weight will have one projection along UN, which is downward, like this. And you have also a projection along UT. The projection along UT will be equal to mg times sine theta. Sine the angle theta, which is between the horizontal and the inclined. So I will write it as a general rule here. So it's mg sine theta, and here theta is 45. So mg sine theta equals to m80. Okay, so if I simplify m, I get that AT is g sine theta. Okay. And in particular, this is why at A, in the first example, A was at the horizontal level, so theta was 0. This is why sine theta was 0 and AT is 0. But at any other position, you will have a certain tangential acceleration AT, and it's due to the projection of the weight. And you know that in a ski application, what will drive your motion is your weight that is acting downward. Okay? Now, once we obtain the two equations, we can solve for the normal and for the acceleration, for the tangential acceleration. Okay. Now, another important thing, if they didn't give me the velocity v, how can I find it myself? So if they just tell you that you are at this position and find the velocity, knowing that they will give you an initial condition. For example, they will tell you, knowing that it was at rest, at the initial, when starting motion, it was, for example, at x equals 60, let's say. So for x equals 60, we know that, for example, velocity was 0. And then how to calculate the velocity at any other position? Do you have an idea what should we do to calculate the velocity at any position if we know just one point, the velocity at one point? Look, in chapter 12, we learned together that we always, when we have, let's say, a velocity at one point and we want to find velocity at another, we should try to relate it to acceleration. Here, we don't have anything about time if you want, but we know positions and we are comparing at two different positions what will be the velocity. So try to remember what are the relations independent of time. The relation that is independent of time is AT ds equals to VdV. Okay, so you know that AT ds equals to VdV. And we derived together now that what is AT? AT is G sine theta. So you can replace AT by G sine of theta. So G sine theta ds equals to VdV. So now, as you can see, if we do separation of variables, so here we have ds and here we have v. We can solve, but in this problem, the variables were x and y, and you don't have the variable s. So you can do a smart thing, is to say, what is ds? ds is, let's say, the elementary motion along the curve. So if I want to find a relation between ds and dx, I can do it, or dy. How to do it? Let us draw the small elements of motion. If this is ds, this will be, so ds, let's say downward. This is dx, and this is dy. And theta represents what? Theta represents this angle here. So you can easily relate ds and dy through theta. Okay? You can write that dy is ds sine theta, but do you think that I should put a minus before it? So is dy equal to plus ds sine theta or minus ds sine theta? To know this, you should look at the variation of y and s. As s is increasing, because ds is counted positive downward, y will be decreasing because y axis is positive upward. So as you will move down on your curve, s will increase and y will decrease. This is why dy is minus ds sine theta. And if you look at your expression, you have ds sine theta here. You have that ds times g sine theta equals to VdV. So now, if you just replace ds sine theta by minus dy, what do you get? You will get minus g dy equals to VdV. And now you can perform your integration between any two locations, since you know your one boundary condition. So at x equals 60, you can get easily y. You replace x by 60 in this relation, so you get that y is 60 squared over 60. It's 60 minus 15 is 45. So you can find at any location then, since y is a function of x, for any known x, you can find its y. And then you can integrate from y at the initial point, from y0 to any point y, and here you integrate from 0 to v. So this will allow you, this equation will allow you to calculate your velocity at any position. Okay, so you see that in general in dynamics, you can combine chapters. You don't have separation of chapters, so you will need sometimes chapter 12 to get, let's say, your velocity, and then from your velocity, you can get an by doing v squared over rho, and from an, you can write your Newton law equation to get unknown forces. Okay, so this is chapter 13, as simple as that. If you just understand well chapter 12, chapter 13 will be very simple. Just you should draw the free body diagram in an appropriate way, put your coordinates well, and once you do this, you do projections and you solve for your unknown forces. Any question on this? So we are done with chapter 13. We continue next time. Okay? Bye.